Good day, ladies and gentlemen, and you're all very welcome to today's session. We are proposing to have a talk by Mark Creekwater, who has been involved with some of our discussions, over the years. Basically, today he's due to talk about theoretical work by Ernest Sternglass. So Sternglass describes the structure of all the particles discovered in the last 100 years as combinations of relativistic electrons and positrons. And here's the point, with no reference to quarks. So that's what Mark is going to talk about. Now, as usual, we have people participating in the green room, and I'll bring them in for a fuller discussion later. And we also have people... I have a private chat here. Yeah, strange echo at my end. I'm not quite sure about that. We'll have to deal with that. We have people participating through the social media, and those of you who've been looking at the comments which you've been getting in recent weeks will note that. There are quite a number of people making a lot of comments and having discussions between themselves, maybe questioning a lot of the fundamental bases of physics. They might be considered as part of the dissident community. And then we have quite a number of people who are countering that and are basically saying that what the mainstream are saying is mainly correct, actually, and we're in error, and that's to be welcomed. I mean, we're in for an open discussion. We want all viewpoints. We're not censoring any viewpoints at all, and that's the purpose of these discussions. No echo from me. From okay, Now, anything else I have to say? Well, the bad news, I better be quite frank with you here, is the speaker hasn't appeared yet. And I'm rather surprised at that, because I did invite him to come in a bit early so we could go through some of the ropes. He hasn't used, I think, the StreamYard system before. So we hope that he'll come in. I know there's a time zone question. He's in Phoenix, Arizona, and that might be Central Time or Mountain Time. I'm not sure, but it's certainly not Eastern Time. And I think I quoted 10 a.m. Eastern Time. He might have thought I meant 10 a.m. his time. But I've also sent him an email, which he hasn't responded to as yet. I sent him that about 10 minutes ago. So I tell you, we have a couple of things in as a fallback. We could maybe show a video or two. However, we have James Keane here, and we also have Laura Gardy, who actually came in through the social media, and she asked me was it possible maybe to get in more directly, because she has some experience with regard to Mark's work and so on. So I said, why not come in over the green room? So at present in the green room, we have Dennis Allen, we have Laura Gardy, and we have James Keane. We also have a person, Jim D.O., whom I haven't met before, and it says his devices are not connected. So I think before sort of making an executive decision as to what we might do, I'll just bring you all up, if I may, gentlemen and madam, just to get your advice. Do you think we could absorb a full 2 hours in discussing this whole question of electrons and positrons without quarks? Or it is quite possible that Mark will appear shortly. But Nick Percival, by the way, who has quite a number of videos on his site, and I've arranged with him to have maybe a few fallbacks in case this happens. But unfortunately, Nick is not here at the moment. So I don't know if he's going to appear today.
Hello,
what do
fractal
you
woman.
Sorry, yeah, Denny, what do you say?
I have some particle modeling that I could talk about if Sternglass particle modeling, if there's no one to present that.
So
I have
how
some
long
particles.
would that absorb? An hour or less?
Well, yeah, I would absorb an hour. I think so.
Okay.
And you the the issue of foundations of science that the first part of the article appeared in, and you could show that as slides.
So you have the slides there, do you?
Well, I have the paper. I can send it to you if you're.
Okay.
And it has diagrams in it and so on, and I have an alternative particle modeling. I model protons, positrons, and electrons and neutrons.
I know you started some of this work with the late David Bergman many years ago, and you've continued yourself. So I am familiar with some of your work, although I'd love to hear it. So that's very generous to be able to step in at the last moment. What do you think about that, Laurie?
I could, because this is supposed to be about Sternglass, I could maybe give you sort of an overview of what I can remember off the top of my head, the important points. And also I have a story to tell about Sternglass himself, because I met him not personally, but on the phone, thanks to Mark Creekwater, because he had Sternglass's email and phone number. And so, I could just tell you about that conversation. I think it's really cool that I met someone that met Albert Einstein, because he met Albert Einstein as an undergrad, and he had this theory about what happened before the Big Bang. That is the name of Sternglass's book. You can see that before the Big Bang, yeah. Right? So this is a book that I keep by my desk all the time. This is like my little, I don't know, my good luck charm or something. I always keep this book. That's why I was so excited that that Mark was going to be doing this. It's disappointing that he's not here, but yeah. So I don't know if you want, I could tell the story right now, or we could wait till later, whatever.
Well, how long roughly would it take maybe for you to tell the story and say the other thing you were going to say?
I don't know, 10, 15 minutes, 20 minutes, maybe at the most.
Oh, okay. Well, what do you think, Jim, of the proposals there? Could we take both of them?
Well, I think it's great that we have a new participant that we haven't seen before, Fractal Woman, and I welcome her and would love to hear her thoughts, which are on the topic of the day today. And it could be that Mark will get your email and chime in at later in our 2-hour session. I might note that my own work accounts for all of the 3 generation of hadrons and mesons, and I could present some of that too. But I don't want. But I would rather we stick with the topic of the day, which Fractal Woman appears prepared to do, and I look forward to hearing from her.
Okay, that sounds very rational, and I'm glad the echo is gone in your system as well.
Yeah, no, I had the YouTube running from when I asked you the chat, and then when I ran this, it ran the StreamYard. So I had both running at the same time, and the YouTube one has a delay. So I was hearing the delay. That was my bad. Yeah. I'm glad I figured that out. Before. Yeah, it sounded very weird, but
okay. Yeah. Well, why don't we do that? Why don't we invite you, Laurie, for 10 minutes or so to give us your explanation and your information and your experience and so on, and then we perhaps take up Dennis's very kind offer to give a talk, and on the basis that we may be interrupted in the event that Mark appears, but if not, we'll continue and we'll have a bit of a discussion at the end, and we should absorb the time. So is that acceptable?
Sounds good.
So I'll bring Jim down. I'll bring Danny down, and I'll give the screen to
Lori. Yeah. Okay, so I am on the hot seat here and totally, completely unprepared. Okay, so what I'm going to do is first I'm going to tell you the little story, my little story with Ernest Sternglass, because Mark had given me his phone number. He said, you should read this book. He told me I should read this book. And so I got it on Amazon, and then he gave me his email address and his phone number. And so Ernest Sternglass was an undergrad when he met Albert Einstein. So he was working on this theory when he was quite young. He was an undergrad. He had just got his undergraduate degree. And he wrote Albert Einstein a letter and said, I'd like to come talk to you about my theory. And Einstein invited him to his home. And he sat in his garden in his backyard, and they talked about his theory, and they talked about, the world and stuff like that. And I think and this is a lot of this is in his book. So I think the most interesting part of the story that he tells in the book is that when he was about to leave, end the day, imagine having a day chatting, physics with Albert Einstein, like that would be the highlight of my life, that's for sure. Anyway, so he, Einstein asked him if he was going to go on to graduate school. And Ernest Sternglass said, yes, I plan on going to graduate school. And so Einstein actually discouraged him from going to graduate school. He said it would basically destroy your curiosity. And, basically he told him to get a cobbler's job. And by cobbler's job, just a job that's sort of kind of easy, and then spend your time and make your mistakes in private is what he said. So let's see. I think I have something here. So here it is right here. Thereupon Einstein asked me whether I intended to continue working so he worked in a lab, and whether I planned to go back to school for an advanced degree in physics. And I answered that I was thinking about graduate school. Okay. And he said, I was absolutely astonished to hear his reply. He urged me to remain in my present job doing applied physics and not go back to school for a doctoral degree, where he suggested I would have any originality crushed out of me. That's what Einstein said to him. He asked me to think about this very carefully and not to go to academic world of teaching, to study on my own what was of interest to me, he's talking about himself, and to work on his ideas about fundamental problems of theory of physics in my spare time, so I would not have to worry when I came up without any results for long periods of time. Thus, I would be able to work and make my mistakes in private. He said, don't do what I have done. Einstein said to him, don't do what I have done. Always keep a cobbler's job where you can get up in the morning and face yourself and doing something useful. Nobody can be a genius and solve problems of the universe every day. Don't make that kind of mistake. When I accepted the position at the Kaiser Wilhelm Institute, the University of Berlin, I had no duties really. So nothing to do except wake up and solve problems of the universe every morning. Nobody can do that. Don't make the mistake I made. So Einstein encouraged you not to go to graduate school, which I thought was really interesting. So that was like the best part of the book for me. That's why I keep that book beside me, because that's what I'm doing. I have a cobbler's job. I work in the field of medical imaging. I develop software. I'm a computer scientist, and I develop software for medical devices. Okay, it's not an easy job. It's not a cobbler's job, but to me it is, because I've been doing it for so long. I can do it off the top of my head. I can spend all day working, and I can come home and work on my own theories of the universe in my own time and make my mistakes in private. And so I really took that to heart. It was very encouraging for me because I do not have a graduate degree, even though I work in academia. I have like 80 papers with my name on. I co-authored 80 papers in the field of medical imaging. I do not have a graduate degree. I never really wanted one. I just like working. I'm a worker bee. I like working. And so that made me feel better about not getting a graduate degree, hearing that from the man. And so, so that's Ernest Sternglass. That was his experience. He did go on to get a graduate degree, and his area of expertise was the effects of radiation on the human condition. Okay, so he studied that. And so back in the day when Japan was building Fukushima, he actually went to Japan and tried to discourage them from building Fukushima, because he knew of the terrible effects of, if something went wrong, that would be a big problem for the human condition, for the human being, for the body. And so when Fukushima happened, I had Ernest Sternglass's phone number. I knew that this was his area of expertise. And my daughter was pregnant with her first child at the time. And so I was really worried at the time. I was really worried about her and the baby. And I just wanted to get his advice. Actually, that's why I called him. So I called Ernest Sternglass, and he surprisingly picked up the phone. I had no idea if he still had this phone number, if he was still even, alive, to be totally honest. I didn't know, but I called and he answered the phone, and he was so kind and gracious and talked to me about what he knew. And I asked him if there was any advice he could give me or my daughter. And the one thing he said she shouldn't drink cow's milk. And the reason for that is because the heavy radioactive particles fall to the ground. The cows eat the particles. And so the problem isn't really the radiation. The problem is with the radioactive particles. And those radioactive particles can go into the milk and then end up in the milk. And so so that was actually the biggest advice that, because obviously there's nothing you can do about it. Fukushima happened. He tried to discourage them from building it. It must have been really disappointing for him when that happened. And so that is, and I think we talked about other things in retrospect. I wished I had recorded that conversation, because that would have been a very cool conversation to have, in my back pocket on, my YouTube channel, whatever. But I didn't record it, unfortunately. And so that is just, my memory of the conversation. We did talk a little bit about his theory and his book, but it was so long ago now, I don't really remember the details of it. And so that's the story. Now,
so okay. Laurie, sorry if I'm interrupting, but
that's fine.
If you haven't told us all, it's fascinating what you've just said, but if you haven't told us at all, could I ask you maybe to come back during the discussion, because Mark has arrived.
Yay!
That's okay. You're happy
as
well.
That is perfect. I got to tell my story. That's why I came here. That's exactly what I wanted to do.
And Mark heard most of it, by the way. I didn't stop you. I said, Mark, we said Laurie's going to speak for about 10 minutes.
Okay.
So let me remove you, and please do come back during the discussion. Thank you very, very much for.
You're welcome. I bought you some time.
You did. You saved my life, actually. So the important thing now is to bring our speaker up today. Mark, good day to you. Great to have you. Great to have you.
Hey, Sue, it's working on your computer, but not on mine. I think because mine's too old. My computer's so old, I can't even get you on my computer, but I'm using my sister's computer.
Okay. Uh-huh. Because you did say to me you weren't familiar with the StreamYard system. So I said, well, look.
What? Oh, that's right. Well, everything's working fine. So let's get on with the presentation.
Let's do that. So I have introduced you very, very briefly, but I didn't know very much about you. So if you want to spend a minute or two before you.
Yes, I would. I want to tell everybody how I came to learn about Sternglass.
Yeah.
Hey,
yeah.
Sue, get the extension cord so the power stays on. I want to tell everybody how I discovered Sternglass's work.
Yeah. Okay. You are moving around a bit, so
yeah, I want this sign to be in here while I'm describing the story. That's what the presentation is. Everybody can write down this if they want while I'm narrating the story of how I learned about Sternglass. Okay.
So I'll leave you to your own resources, and I'll only pop in if absolutely necessary. You do know that we'd like you to speak for an hour or so. You can speak for more if you wish, more time.
No, I want to speak for about the last 10 minutes. I want to look at the comments and answer them, and then open the discussion.
That helps me.
I want to speak for about 40 minutes.
Speaker. Yeah. So I'm going to put myself down now, and I'm going to leave you as the sole presenter, Mark, and thank you very much.
Okay.
You do know that this is being recorded, by the way, and
yes.
the first few minutes, what I said about you, which is very little, except acknowledging
yes.
that you were here to talk about this subject.
Yes.
You'll be able to see in the recording.
Mm-hmm.
Okay, it's all yours now.
Okay.
Sorry, it's all mine. Sorry, wait a minute. At the stage, I've made.
Okay, everybody. I'm Mark Creekwater, and I'm going to talk about Ernest Sternglass and Menachem Shimoni. Mainly Sternglass this week, and then Shimoni 2 weeks from now. And while I'm telling you how I discovered Sternglass's work, you can copy this down if you want. I was about 2003. I started studying astrophysics, and I would read a book, and a physics book. I read dozens of physics books. I read all the best authors. John Archibald Wheeler, Lee Smolin, the trouble with The Trouble with Physics, which is a very good book. I recommend. Kip Thorne, Black Holes and Time Warps is another good book I read. In other words, I read dozens of books, and every single one of them, I'd get stuck about halfway through the book where they started talking about quarks and things like supersymmetry and symmetry breaking and all kinds of stuff that I just couldn't understand. And I was afraid that I just wasn't smart enough to understand modern physics. Well, after several years like this, going on, not understanding any of the books I was reading, I found Sternglass's book in the main library in Berkeley, downtown Berkeley, USA, Berkeley, California. And I read Sternglass's book all the way through to the very end. He uses nothing more than high school algebra, which is totally understandable to me. And that's how I discovered Sternglass's work. And about another year later, within the next year or so, I discovered Shimoni's work as well, and on the internet. And it's all there. He wrote 3 books, but most of what's in the books is also on the internet, so anybody can learn about his work. So now I want to change this thing here, and you can copy down this information if you want. These are let's see if I can. These are two of my essays that I recommend that you read. I posted these before, and I have a feeling that many of you have never read either one of them. All the math is easy math. Nothing more complicated than high school algebra. And I get some amazing results. A proton radius comes out exactly like they get when they measure it, when they do experiments to measure the proton radius. It always comes out to around 0.87 of a Fermi, 0.87 times 10 to the minus 13 centimeter, 10 to the minus 15 meter, you get the same answer using high school algebra. I do using Sternglass's theory. And this Larmor precession calculation, I'm especially proud of that. This, I think, is my best one, especially Appendix D. If you read this at all, be sure to read Appendix D, which is a really cool result. Anyway, you'll have to read this to see why I feel it's my best essay. And so I want to talk about Sternglass's proton model. According to Sternglass, in his book, before the Big Bang, I don't know, can you see that? Before the Big Bang is what his book looks like. And in his book, he describes the structure of the proton in the last chapter. And the entire book leads up to the last chapter. And in his model, he says that there's 4 electron. He makes no references to quarks. He talks about quarks in the book. He knew a lot about quarks and quark theory, but he describes protons. He says quarks are actually made of smaller particles, relativistic speedy electrons and positrons, which are known to exist. In other words, relativistic electron-positron pairs. And these are what actually quarks are composed of, these smaller objects, which are relativistic electrons and positrons. And a proton is 4 electron-positron pairs. You have an electron and a positron. They orbit around each other. And Sternglass described this in a paper published in 1961, July 1st, 1961, in the Physical Review Journal, one of the most prestigious physics journals. And in it, he describes an electron-positron pair. He says that's a pi mason. The pi mason had been discovered 14 years previously, and he said the pi mason is nothing but an electron and a positron orbiting around each other at almost the speed of light in a very tight orbit, about 0.7 Fermis, 0.7 times 10 to the minus 13 centimeters. And that's what a pi mason is. And this was before quark theory. Nobody had ever announced quark theory until several years after 1961. And keep in mind that the inventor of quark theory, Mary Gell-Mann, he said many times in many different ways that quarks might not actually exist. They might just be mathematical tools to describe tiny objects. He said one famous quote that I have in my book, is that a famous quote is that quarks might go away after a while when we learn to solve our equations without using quarks. He always thought that they might be mathematical tools rather than real objects. And add to that the fact that quarks have never been observed in a physics lab, which is a well-known fact. And they invented a theory, a reason why you don't observe quarks. And supposedly, it's like a rubber band. If you have 2 quarks, you pull them farther apart, they're more attracted to each other. Supposedly, that's the way quarks are, and that's why you don't see them. They never come out. But Anyway, I prefer to follow Sternglass in saying that there's really no such thing as a quark. It's all electrons and positrons. In Sternglass's model, he says there's 4 electron-positron pairs around the outside of a proton, and then an unpaired positron at the center, which is spinning. Or no, according to Sternglass, that the 4 pairs are in the form of a letter H, and the positron at the center does a figure 8 orbit like this. Well, I'm pretty sure that's incorrect. I've modified his theory and saying that they're actually arranged this way, like a tetrahedron. The 4 electron-positron pairs around the outside are arranged like a tetrahedron, and the positron at the center is spinning, but it's held at the center by magnetic trapping, which is something physicists know how to do in physics lab. They use 4 magnets to hold a charged particle in place. Well, perhaps Mother Nature does this with the proton. I prefer to think that if I were God or Mother Nature, ask yourself this: what would you use to build a universe? What shape would you use? Naturally, the tetrahedron is the strongest and simplest 3-dimensional shape. You would naturally want to use that for a structure of protons and neutrons. So that's all in my paper about protons and neutrons. Let me see if I can find that. Oh. Yeah, the structure of protons and neutrons. I hope everybody can see that. And you can copy down that if you want. That's the link if you want to read that, which I recommend. I hope you want to read that. And the other one, of course, those are the 4 I would prefer you to read if you read any of my essays at all. In the structure of protons and neutrons, I use simple formulas you find in any Physics 101 textbook to calculate magnetic moment and angular momentum, which is also called mechanical moment. Also, another old-fashioned name for angular momentum is mechanical moment. So I use simple Physics 101 formulas to calculate mechanical moment and magnetic moment of the. I use that information to create 2 equations, which I solve simultaneously to determine the size of the electron and positron at the center of a neutron. And by another method, which Sternglass never used. Sternglass never did that, and he also never used the other method, which I used to determine the mass of the electron-positron pairs around the outside. And using that, I determined the size of and the structure of the neutron and the proton. And it's approximately a diameter of 2.8 Fermis, 2.8 times 10 to the minus 13th centimeter. So that's Sternglass's proton model. The other main part of Sternglass's theory, I hope everybody got the information they need here. The other main part of his theory is he talks about what happened before the Big Bang, what led up to the Big Bang, and then what happened at the Big Bang, and at the Big Bang, according to Sternglass, all the neutrons which exist were created. The neutrons quickly decay to protons. So his theory explains the birth process of protons and neutrons, which, as far as I know, is still a mystery to the Standard Model. And also, he says that, what's the other thing? Oh, he explains the source of the immense amount of energy. It's binding energy, which similar to what happens when water freezes and forms ice. It gives off binding energy, the same amount of energy you need to melt the ice. Well, it's a phase transition when water changes to ice. And what happened is Sternglass's theory, you had a bunch of particles, each about the mass of 5 protons, and they did a phase transition similar to, and he compares it in his book, he compares it to what happens when water freezes. It gives off a huge amount of energy, which not only the phase transition forms neutrons, which decay to protons. So that explains the birth process of protons and neutrons, as I already mentioned. And the binding energy that it gives off with this phase transition, which is similar to when water freezes and forms ice, gives off binding energy. Well, is the source of the immense energy, the Big Bang. Well, he says that that's how everything got started. Well, how did it start before the Big Bang? That's the really interesting part. A Belgian priest named Georges Lemaitre, in about 1930, he published a theory called The Primeval Atom. And it's a book by that name, published in 1930. And by him, where he says that our universe started as a single atom. He calls it the primeval atom, and Sternglass uses the same term. He adopted the term from Lemaitre, and he says this huge atom consists of nothing but an electron and a positron, each containing half the mass and energy of the universe and orbiting around each other at the speed of light. So their electromagnetic field, their huge electromagnetic field, is moving at about almost the speed of light. Well, because the electromagnetic field is so large, that means it takes trillions of years to go around one time. Anyway, when it goes around one time, it divides in half, and then each of them keeps going around. It takes another few billion years, and then each of them divides in half, so you have 4 of them. And every time it divides in half, the mass, of course, decreases by half, and the radius decreases by the square root of a half, by the factor of square root of 2. So it keeps on doing this. After only 270 generations of this kind of dividing in half, you would have 2 to the 270 of these tiny objects, each about the size of each about the mass of 5 protons. Well, that's when the phase transition, or shortly thereafter, after a few more dividing in half events, the phase transition takes place, and that's how the Big Bang starts, from one single atom that produces all the rest of the atoms. Sternglass calls all of these objects, from the very largest, the primeval atom, down to pi masons and even smaller, he calls them cosmological systems. And every cosmological system, the mass is proportional to the square root of the radius, or whatever. The radius is proportional to the square root of the mass. So half the mass, it'll be square root of 1/2 of the radius. So anyway, that's how each of these cosmological systems is exactly the same shape, from the very large ones to the very small ones. Just the only difference is in scale. And a very large one will create an entire galaxy after it divides down and explodes. And that's what dark matter is. There's a lot, they didn't all explode at the same time. He says in his book that at the time of the Big Bang, it was like only about 1% of the mass of the universe actually exploded. The rest of it was still embedded in the, like raisins in a cake, he says, like raisins in a cake. The whole thing exploded. And the ones that are embedded in the cake, they're all flying outwardly. That's what dark matter is. These things are totally invisible. The only way to measure them is by gravity. They've tried that by very gravitational lensing, but they still haven't figured out what dark matter is. It's not small particles. It comes in large masses. A lot of the researchers have speculated that dark matter is tiny. It's not. It comes in large chunks, according to Sternglass's theory. And they're totally invisible, and so that they're lurking in space, millions of them all the time. And they're slowly dividing in half again and again and again. They're doing this countdown to another Big Bang. But it's just like the Big Bang, only smaller. And Sternglass calls them delayed mini bangs. He says, according to his theory, there must be delayed mini bangs happening all the time. Well, guess what? Astronomers have been observing them since the 1960s and calling them quasars. That's what a quasar is. It's a bit of dark matter that it stays invisible, lurking in space, and then at a certain point in the dividing half process, in its own lifetime, it'll explode, just like a fireworks display, and it becomes very visible. So that's what quasars are. Now, I'd like to, I don't know, were there any comments? I want to go to the comments now and see if I can answer some of them. So I want to go back to.
I might be able to help you here because a lot of them are just to and fro conversations. They're not really.
Well, I got it now. I am also a fan of Shimoni's coal model. Well, that's good, Fractal Woman. Fractal Woman and I have known each other for years. We're Facebook friends. I wanted to go up and visit one time, but I could never get a passport into Canada. You know, it takes forever to get a passport, which really is kind of stupid, in my opinion. So Fractal Woman says, in my theory, the tangential velocity of electron positron spinning pair is the speed of light. Exactly. That's exactly what Sternglass says. So magnetic moments of protons and neutrons. Oh, nice. I'll definitely check out those references. Thank you. The Big Bang was a phase transition. Exactly. Thanks for the links. Okay, now I'd like to open it to question and answers.
Right. Well, let's just get things a little sorted out now. I'll just bring you down for a second. So, thank you very much for that. And I'm interested that we had no death by PowerPoint. We had rather the real thing, you know, in black and white on boards. And we've tried to paste some of the links into the chat so you'll be able to retrieve those yourselves. But if the worst comes to the worst, you can obviously pause the recording at any particular spot and take down what Mark has said. If necessary, we can get more information from him. Now, yeah, I'm particularly interested in the question of the explanation, if you like, of the Larmor precession. And I was also aware of Gelman's comment that perhaps the quark is not a real physical particle and is more a mathematical construct. I mean, he did say, after all, that that which is not forbidden is obligatory. So it was maybe a bit of an extrapolation, and perhaps people aren't aware of that sufficiently. So what we'll do, with Mark's permission, is we'll devote. I'm just seeing are there any new comments coming in. Links to your book, yeah. spinning electron. We'll devote a little time to general questions, maybe dealing with questions which have come in on the comments. And then I'll open it to the green room. Now, we have a number of people in the green room, and if you have anything urgent you'd like to say, just wave your hand, because I can see you all and I'll bring you up. But if you don't do that, I will bring all of you up. Yeah, you want to come in, Mark, immediately. I'm hogging the conversation. I'll bring you in a second now, but just you'll have plenty of time. So I just want to say that one of the penalties of being in the green room is you are asked to contribute and make make some conversation with the speaker and so on. So we will do that. So Mark, if that's all right, if we could spend a few moments just checking whether there are any comments which haven't been dealt with sufficiently. So you just see that now.
Yeah, I want to say something. I forgot part of the presentation, but I want to answer one of the comments first and then do the part that I forgot, okay? So the comment I want to answer from James Keene, why the spinning electron positrons do not attract and combine. It's because they're even though they're very close, they're spinning at such a high rate of speed that the centrifugal force exactly balances the electromagnetic force. That's what Sternglass described in his 1961 paper. And dang, I see I should have turned my mustache. I didn't realize how it would look on TV. But anyway, that's why they don't attract and combine. Another reason, that inside the neutron, there's an electron positron, and they're spinning, but they're not orbiting around each other. They're spinning like two disc-shaped magnets. They're attached to each other and are spinning around the same axis. So, and because one's positive and one's negative, they generate magnetic fields which oppose each other, which prevents them from annihilating. So that's why a neutron is stable for about 8 or 10 minutes before the electron flies off in space. It's metastable, they say, the neutron. And that's why they don't annihilate when they're in the center of the neutron, the electron and the positron. I calculate that in my paper about the structure of protons and neutrons. It turns out the electron has a larger radius, even though it has a smaller mass. That's really interesting too. So that's why I hope you'll read the paper. And the part that I didn't in the presentation, this is Sternglass's formula. He says it's a solution to the Klein-Gordon equation. And I have no idea where he got it from. I never would have found it. It's not in his book. It's in his papers that are published in 1965. Can everybody see this and read it?
Yes, it's clear enough, Mark.
Okay, and it's the most complicated equation that I use in any of my papers, but it's still fairly easy to use if you know how to deal with exponents. So that's the formula he uses in his 1965 papers, 2 of them. He uses this formula and the idea that the electron-positron pairs are pi mesons. He uses this to describe the structure of every single one of the particles that were known at that time, which were dozens, maybe 100 at that time. Now it's even more. He uses his theory and this formula to show the construction, the structure of all of the tiny objects which have been discovered since the last 75 years. And I checked his math and found it to be exactly correct. He's got in each of the papers a long chart of dozens of different, pi mesons, mu mesons, also called muons, K mesons, rho mesons, lambda, sigma, all of them, hyperon states, all kinds of different subatomic particles. He uses his theory to calculate the mass and the spins and lifetimes of these objects. And I checked his mass, and they're exactly correct. When I changed his methods in any of several different ways, I obtained numbers that made no sense. So I satisfied myself personally that Sternglass is absolutely correct to describe the structure of all the subatomic particles using his theory. However, with the exception of protons and neutrons, he never uses this formula. He never does anything where he uses this formula to describe the structure of protons and neutrons. He describes it in his book and in some of his papers, but without using any kind of exact formulas. And
so Mark,
I've used this formula to calculate the structure of protons and neutrons, assuming they're tetrahedral, and that's in my paper, The Structure of Protons and Neutrons, which I hope you guys will read.
Right. Mark, with your permission, I'd like to start bringing in some people from the green room to have a discussion and ask you some questions. Great. Of course, if there are any other questions coming in on the chat, we can come back to them. We haven't cut those off. Now, in particular, Dennis P. Allen Jr., he was very kindly going to give actually a talk in the event, which didn't materialize, thankfully, that you didn't appear. Because Dennis, I hope you're there, Dennis, but you've done some considerable work on particles, particle models, and spinning rings. You started working with the late David Bergman many years ago, and you've continued and you've extrapolated a lot of that work to the elementary particles. So have you any observations or any questions or any comment to make to Mark on the whole subject?
Well, Dave Bergman and I have modeled electrons, protons, positrons, and neutrons. And you mentioned that I think it was a pi meson you said was an electron and a positron involved electron.
Exactly.
It's two disk magnets.
What?
You said that they were like two disk magnets right next to each other.
That's right. They spin. Sternglass explains it this way. He says there's two different possibilities. They can either spin in the same direction or they spin in the opposite direction. They're orbiting around each other, but there are two possibilities. They can spin in the same direction or opposite directions. If they spin in the same direction, that's the known pi meson. According to Sternglass, there's another pi meson, is theoretical, where they spin in opposite directions, and that's unknown. It's theoretical. There's been evidence. One of his colleagues back in the 60s found evidence for its existence, and I cite that in my papers, but it's not regarded as a real particle by the physics community. There's no evidence, not enough evidence, but I'm pretty sure that it exists. And that's the one that Sternglass uses as the basis for all of the structures of the tiny subatomic particles.
Well, you mentioned, I think it was in the case of a proton, maybe, that you had two electron and a positron, and they were like disk magnets. They were spinning.
Yes. That's inside the neutron.
Yes.
They're like two disk magnets. They're locked onto each other because of their electrical attraction, because one's positive and one's negative, and are spinning in the same direction, so they're generating a magnetic current, which keeps them from annihilating. That's why they keep on spinning for 8 or 10 minutes, and then the electron flies out. That's why the neutron is semi-stable.
Yeah, well, my Bergman and I's and my particle modeling involved spinning rings of charge, very thin torus
Yeah,
of
yeah,
charge.
yeah. I wouldn't
And,
doubt that
that
possibility
would
at
seem
all.
to agree with what you just said, that they're like disk magnets. That's exactly it in our
Yeah,
proton and positron modeling.
the electron and the positron at the center of the neutron.
Yeah,
Normally,
well,
a proton has a positron at its center, and if you add an electron, it becomes a neutron.
well, the point I'm trying to make is that my modeling seems to have something in common with you and Sternglass's modeling, in that
Mm-hmm.
my modeling is of a proton, a positron, and an electron. Mine and Dave's model is a spinning ring of charge. In the case of an electron, it's a spinning ring of negative charge.
Mm-hmm.
Which
Yeah,
is,
I wouldn't doubt that.
okay. So I get a radius for the electron. Actually, Dave and I got it. What is your radius? I want to compare your radius
Well,
of
the
an electron.
radius it varies. The electron at the center of a neutron, it's 0.8. I'm trying to think. It's 5. It's the positron is 587. The electron is 811. I think 0.811 Fermis.
No, I'm talking
Is your
about.
system considerably bigger? Is your
Something like
system
that.
considerably bigger than the
Yeah,
conventional
it's
view?
bigger than the positron, but smaller mass.
Okay.
Well, if you have a free electron, just one electron in space,
Right.
what do you
What
calculate
is it?
the radius
Okay,
as?
it would they say the classical radius of the electron is 2.8 times 2.8 Fermis, but also it has a Compton wavelength, which is 2 point or whatever it is, something times 10 to the minus 10, 2.43, 3.24, something like that, times 10 to the minus 10.
Well, what Dave Bergman and I got was 3.87 times 10 to the minus 13 was the
3.87.
yes.
Yeah. 387 times 10 to the minus 13. Yeah, that's interesting. That's interesting. That's close to 2.8. You said 3.8.
Yes.
That's only a little bit bigger than the classical electron radius in classical theory.
So we seem to be in the same ballpark anyway, yeah.
Yeah.
Okay. Well, that is quite interesting. Are you familiar, Mark, with some of the work that was done by Bergman and by Dennis?
No.
Oh, okay, because I don't have any references you might give Dennis.
Well, if he gives me his email address, I'll send him. Well, you have his. You must have his email address, Ian. Do you not?
I do.
You send it to me, and yeah, I can't.
Can you see it?
Not clearly enough to write it down. No, but Ian has it.
Yeah,
and he'll send it to me.
I'll send you the email address. Yeah, Compton wavelength. Yeah. Okay. Well, are there any other observations at this point that you want to make, Denny? You can come back, of course, because we have practically an hour left, 50 minutes, let's say, for discussion.
Well, I also model the proton. Dave is dead now, but I also model the proton as a spinning ring, only a positive charge.
Mm-hmm.
And I get a radius for that. And then I model the positron and get a radius for that. And a neutron is a proton and an electron, but the electron, as you mentioned, is bigger than the proton. And so we have a ring within a ring, so to speak. And so that explains why people think there are neutrinos, because there's a mutual spin pumping of the electron and the proton in the neutron. And that slight increases the energy, which then gives you, they postulate that it's a neutron because they believe that energy has to be conserved. And so this little extra energy has to belong to something or other. And they call it a neutrino.
Right. Yeah. Yeah. Okay. I think neutrinos they're like photons with half energy, half a angular momentum. But
Well,
although they're said to have mass, I don't understand that theory, why they have to have mass. But
it's for
I think
conservation.
they're very close to being mass, very close to being photons. But and photons actually have mass too, as we see.
Yeah. But neutrinos, the deeper they go into the earth in salt mines or whatnot,
Right. Yeah,
the
they
less
penetrate anything.
neutrinos they pick up. So that it seems that there are no neutrinos.
Well, they penetrate. I'm sure they exist. They just penetrate. They have such great penetrating power. You hardly ever see one.
Because I think one of the suggestions is that they were an artificial contrivance, just introduced to balance the.
Yeah, they were, and then it turned out they observed some. I think they're pretty sure they've been observed.
Well, they think they've observed them, but actually, the deeper they go, the less they get, and that shouldn't be, since they can penetrate anything.
Maybe they're photons, like photons with half spin.
I don't think so.
Okay, a lot of it is speculation, of course, but thanks very much for that. So perhaps, Danny, is there anything else before we just move on to the next? I'm just seeing all the new comments coming in.
Well, no, I could go into the Schrodinger wave equation and how to improve on it, its solutions, but that would take too much time, I think.
Well, we may very well come back to accept your very kind offer. You were willing to stand in at the beginning of this session, and we will take.
Well, it looked like nothing was going to happen. I mean.
Right. Well, thank you. No, thank you for that. Okay, so I'll bring you down for the present, Danny. If you have any other points, just wave your hand.
Oh, that's fine. Thank you.
Thank you. And I'd like, perhaps, with Laurie's permission, to come back to her. She's next in line here. So, if I may bring you up, at least you're able to say hello to Mark and in the flesh or virtual.
Hey, Mark, long time no hear.
Yeah.
I was starting to wonder if you're even still with us.
Yeah, I'm 75.
Have you been drinking more Creekwater?
Yes.
Good.
Absolutely.
Was there anything surprising in what he said today, Laurie, or was it an update, or had you heard a lot of it before?
Yeah, that's basically.
Yeah, because she's read Sternglass. She's probably one of the few people who've read Sternglass's book.
Yeah,
well, she told us that at the beginning.
I read it. I didn't memorize it. I did not memorize it, but I
read the whole book.
I read it. It seemed to be in better condition than your copy, which probably meant it was less thumbed, if I may say so.
No, anyway. I mark up my books, right? I mark up my books. I don't know if you can see that, but anyway,
I marked mine up like that big time.
I only mark up books that I like.
Yeah.
So I did have to read it a bunch of times, because every time.
Yeah, same here.
As I become more knowledgeable in this field, every time I read it, I get more information about it.
Exactly. It's that kind of a book.
But you also mentioned Simony.
Yeah. And I'm Simony. I'm going to talk about him next time.
Is it Simony or Shimony? You're
Am I saying it wrong? Shimony?
Shimony.
I would say Simony, but he said Shimony. It's S-H, is it? Okay.
Shimony.
Is that how you say it? Okay, because I never really knew how to say it. Of course, I studied his work as well, and that I actually wrote a paper called "The Medium for the Propagation of Light Revisited,"
Yeah.
which is on ResearchGate, and I mentioned his. He does an interesting analogy with sodium chloride, with salt.
Mhm.
Okay, so what he does, so that model is an electron positron pair model for the ether, right? Or for the medium for the I don't want to call it ether because nobody likes that word anymore. So
No,
I'll
he
get in
doesn't.
trouble when I say that word.
Shimoni hated that word ether
Yeah,
because it makes you
because
sound like a crackpot.
it's been demonized, right? So
Yeah, it makes
I
you
like to
sound like
call
a
it
crackpot.
the medium, which it means the medium for the propagation of light.
Right.
And it is an electron positron pair medium.
Yeah.
It self-organizes into some structure. Now, he says it self-organizes into an FCC structure, but I think that it's better thought of as a tetrahedron. I think it does that. The medium for the propagation of light does self-organize into a tetrahedral structure as well. So it's kind of like part of his theory. Like what I do is I take part of everyone's theory. I take a piece of puzzle from everyone I study. If something rings true to me, I take that and I try to apply it and put it
Yeah,
all together.
it might be tetrahedral.
I think it's tetrahedral.
Yeah,
And
it might
so
be.
there's a new kind of thing that's maybe people do or don't know about called spin ice. Okay, there's a thing called a spin ice, and spin ice self-organizes into tetrahedral structures as well. And the tetrahedral structure can actually scale in a fractal sense. And so there is a fractal structure called the 60 tetrahedron grid, which is a fractal pattern. And so, being fractal woman, of course, I'm very interested in anything that can self-organize into a fractal structure. And so, like Sternglass and Shimoni and so many people, like David Toom had an electron positron pair model, and Don Hodson had an electron positron pair model for the
Even
medium.
Franklin who's not here today, he has one himself.
Who's that?
Franklin Who, do you know him?
Franklin. I've seen. Yeah, I saw him
He
talk.
does as well.
Yeah, I saw his talk. I read his work and saw his talk at the Natural Philosophy Society convention that you guys had in Vancouver.
Yeah, in Canada some years ago.
I don't
Yeah.
know if you're at that, but yeah. So he does as well. So I like anyone that talks about electron positron pairs, I like to talk to or like.
Well, that's the only kind of structure that makes sense.
Yeah. So what he did, what Shimoni did, was he made an analogy with sodium chloride. So when you have a salt crystal, it's clear, right? It's transparent.
Right.
But when you shine a light on it of 8 electron volts,
That's right.
the sodium and the chloride unbind from the medium.
Yeah.
Right. And then the salt becomes cloudy. And then when you take the source away, when you take that energy away, they bind back into the sodium chloride and they emit the energy into the medium. So it's just like electron. So in my feeling about the electron positron pairs is the electron positron pairs, when they annihilate, they're not disappearing. They're falling back into the medium. And the energy that they release, the 2 gamma rays, is the binding energy. Okay, so whenever people don't really realize that when something binds together, the energy is released, right? So it doesn't take energy to bind something together. Energy is actually released when 2 things bind together. So when people think of electron positron pairs annihilating, they think of them as disappearing. But I think of them as that's the energy, the binding energy that binds them together into the medium for the propagation of light. And the 2 gamma rays, of course, go in opposite directions or whatever. And so that's how I see the medium. And that's why they need electron positron pairs. Physics needs they call them virtual. But they're not virtual. They're real. But they're virtual because you can't see them. They're transparent. The medium is transparent, like air is transparent, like the sodium chloride crystal is transparent. You know what I mean? Like it's transparent. But that doesn't mean there's nothing there. And so the fact that they need electron positron pairs and they actually see them, like you can pull electron positron pairs, real ones, out of the medium, but it's very difficult to do out in the middle of space. It's easier to do when you're near a black hole, or it's easier to do when you're near an atom. So they can pull electron-positron pairs out, near close to an atom, but not far away from an atom. So it all kind of makes sense to me from that perspective. There can be a medium, in my opinion. That doesn't mean there is one, but I think there can be one. And if there is one in my paper, the medium for the propagation of light revisited, I do exactly what Shimhoni did. I do exactly what he did.
Yeah, exactly. Shimoni does exactly the same thing.
Yeah.
Let me, Fractal woman, somebody's asking you a question.
If you'd like to address
what's a
question.
spin-up particle? I don't know what that is.
In that, what the speaker said.
He's suggesting there might be a disagreement. I don't know if that's real or not.
What is a spin-up particle? I don't know what that is. What is that?
Oh, he's talking about spin up and spin down.
Well, what's he talking about? The electrons have spin up or spin down. In a pair, the Sternglass pair, it's both. I think one is spin up and one is no. They're both spin up in Sternglass's model. There's two different kinds of pi mesons. One of them is spin up, spin down, and the other one they're both spin up.
Okay. So that's kind of like the quarks then, because you have
and what predictions distinguish your model from a quark model? James Keene wants to know. I'll tell you, I calculated the radius of one of the electron-positron pairs around the outside of a proton or neutron. The radius of the electron-positron pairs is 0.87, almost exactly 0.87 Fermis, which is what they get when they measure the radius of a proton. Well, they think they're measuring the proton radius, but they're actually measuring the radius of one of the electron-positron pairs. There's four of them around the outside of a proton. So if somebody suggests the next time they do this experiment, suggests that maybe you're measuring the radius of an electron-positron pair, maybe they can modify the experiment to see what they're actually measuring. And that would be a prediction. The quark model can't predict that. You can predict that only by visualizing what they look like from Sternglass's model.
Are neutrinos electron-positron pairs?
No. I think neutrinos are similar to photons, but possibly having a little bit of mass.
Yeah, Jim is next, just to indicate that because he's made a signal. Okay, that was a very interesting exchange between the two of you. Anything else you'd like to raise at this point, Laurie, before we go on? You can come back again if you wish.
Yeah.
Anything else?
I want to bring in maybe Jeff Yee to this conversation because he has a model. He has his wave model of the universe, but he also talks about the tetrahedral structure. And so when they discovered the pentaquark, of course, for him everything is neutrinos. That's why I was asking if neutrinos are electron-positron pairs, because in his model everything is neutrinos, and in the proton is 4 neutrinos in a tetrahedron structure, and then there's a positron in the middle or a positive charge in the middle of that to make it a positive charge. So at least hopefully I'm remembering that correctly, but there's also a tetrahedral structure in his model, and I'm very interested in that.
We have had a presentation from him some time ago.
Yeah. So I've co-authored a couple of papers with him, and his work is really good as well. So I just wanted to mention that because of the tetrahedral structures that we're talking about.
Okay.
So, other than that, I'm good.
Okay, well, thank you very much for all those and for stepping in at the beginning as well, Laurie.
Yeah,
so
no problem.
I'll just bring it down for the moment.
Yeah, I have to go right now, so I just I'm glad you got me, and I'm glad I got to say hi to Mark and that I got to do my spiel. So
well, you've been very welcome.
I appreciate it. Thanks so much. All right.
Okay.
Bye.
Now, I'm going to bring Jim up. Because Jim has made one or two comments here. Sternglass experiment is the most recent, and I think he wanted to say a few things anyway. in general.
Well,
about
the
yours.
up and down spins are from the Stern-Gerlach experiment. Okay.
Oh, right.
That was a question that was raised in the discussion a few minutes ago. I'm not sure I got any answer to what predictions distinguish your model from a quark model. I heard a lot of talk, but I didn't get what data distinguishes your model from a quark model.
They when they measure the proton radius, they get this number that in my model, it's not the radius of the proton, it's the radius of a electron positron pair.
And then you say there are four of them.
That's a number that distinguishes it. The quark model can't predict that. They don't have any way to visualize what the thing looks like, what the proton actually looks like.
The radius of the proton has been determined by scattering data.
Yeah, they're not measuring. My contention is they're not measuring the radius of the proton. They're measuring the radius of one of the electron positron pairs. The stuff is scattering off one of these pairs. They're like hard nuggets. They're like the nuggets that they say that quarks are supposed to be like hard nuggets. Well, these are like hard nuggets, just like as hard as quarks are supposed to be. And when light scatters off of it, it measures the radius, but they're not measuring the proton radius. They're measuring the radius of one of the electron positron pairs. That's
but you're
my
saying that the
theory.
proton has four of these. Is that correct?
Four of them are around the outside in the shape of a tetrahedron.
So, and each of the four has that radius of about
Yes, same radius, 8.87 Fermis.
Well, so you're saying that only one of the four gets knocked off when proton scattering is studied? This I don't understand.
I don't know how they did. I don't know.
All four get deflected.
I don't
together.
understand the details of how they do this experiment. Do you? Do you understand?
Yes.
Can you explain the details to me?
Well, basically, the angle of scattering can be used to determine the size of the object. It's like
so if the object is scattering, whatever it's scattering, if this object is not the entire proton, but just one of these electron-positron pairs with this radius, 8.87, that would be the radius they would measure. That's the object that's causing the scattering.
So you're saying that the entire proton does not scatter.
That's right. It's the scattering that they're assuming that it's the entire proton, but the scattering that they're measuring, in my theory, is the one of the pairs, not the entire proton.
So you're saying the entire proton consists of four objects, which are each about 0.8 femtometers in size.
0.87
well,
times
0.87, whatever the number is.
What?
Whatever the number is, 0.87, whatever you want to call
whatever it is, it's a certain size.
And there are four of them in a proton.
Right.
And they're not exactly all in the same spot.
They're in the form of a tetrahedron.
The total size of the proton must be much larger if you've got four of these 0.87 objects.
The size of the proton. Yes, the size of the proton is
contradiction.
The size of the proton is larger. According to this, the radius of the entire proton would be about 1.4 Fermis, almost twice as big, almost twice as much. 1.4 Fermi.
Okay, well, at least in your thinking, that solves that contradiction. The other thing I might mention, if I may, is that this idea of the spinning electron positron pairs depends upon two unexplained observations. One, the speed of light, and two, the value of the elementary charge. And both of those are unexplained observations, so that you use unexplained observations to I guess, make a theory which is unexplained itself.
No, I don't feel that. I think that the charge is given, the fundamental charge is given, and the speed of light is assumed to be about c, approximately c. In
In other words, you
Stern's
accept
model
these
is that you
measured values. You
what
accept these measured values
that
without question.
because those
In
are
other words, there's no need to explain them.
that's right. They're given.
So part of
The
the
speed of
universe
light
we're going
is
to
given
explain,
because
and part of it we don't care about explaining.
it's
We
known
just
from measurement. Well, you can explain why. You can. Maxwell explained why it is almost 150 years ago.
I think the point, Jim, is that you, in your system, you claim, if I may say so, to be able to derive these from first principles. You know that they're unique elements which come out of a basic overarching theory. I think you've done that before. You've indicated that to us. If I haven't misunderstood it, things
yes,
like the
that's
speed of light and the
so.
electronic charge.
I just wonder why these unexplained observations are not the full focus of some effort to explain them, of why they have the values.
Yeah, anybody can do that if they want to. I'm not. Nobody's going to stop you if you want to do that. I just don't feel like it's necessary.
All right. Okay.
Okay.
Thank you.
Okay, Jim. So, is there anything else before we move on? You can obviously come back.
No, that's okay. Thank you, Ian, for the.
Well, thank you very much for your help as usual.
Thank you, James.
Now, there's just one fundamental question which has been put up here, and the second question is similar. You know, he's making a very general statement that since we have more than 60 years of experiments that map the structure of the proton and neutron, none of those results are consistent with the neutron being made of a proton and electron.
Well, how do you explain the fact that when you have a proton and an antiproton and they annihilate, when they come together, it produces pi mesons, and then those decay into electrons and positrons. It's the intermediate decay product is pi mesons, which ultimately the whole thing decays into nothing but electrons and positrons and photons and neutrinos.
Did you say antineutrinos?
Yeah, if you take an antiproton and a proton and they annihilate, then the intermediate product is pi mesons, charged pi mesons, and they decay into electrons and positrons.
Okay. Well, Andrew may wish to come back upon this. I think he has some experience in particle physics.
Well, Sternglass says that in his book. I don't think anybody would dispute that. Sometimes I understand. I think Sternglass says it gives off 3 jets. Come from when you annihilate a proton and an antiproton, it'll give off 3 jets in some instances. I think he says that. I'm not sure. But the jets consist of pi mesons. So that proves that protons are made of pi mesons, and pi mesons we can assume that they're made of electrons and positrons if we believe Sternglass.
Okay, if there, Kev, just a basic question about the uncertainty principle seemingly being at odds with the electron being inside the radius of a proton. He's suggesting
the uncertainty principle. Yeah, I use that. Oh no, I don't use that at all. The only principle I use is Planck's. That the angular momentum has to be a multiple of Planck's constant or half of Planck's constant. That's the only. I don't use any kind of
Heisenberg principle. Yeah.
No, I don't use any of that. An uncertainty principle. Period. I don't use it at all in any of my papers.
Okay. Well, at least we've clarified that from that question. Now there are 2 people whom I don't know, Marguerite and Jim O'D or Jim.
Oh, that's my brother and sister, I think.
Oh, are they? Oh, because they're not connected. I think Marguerite came in for a moment or two. I mean, they're quite welcome to come back because we have the space. But one of our regular contributors, whom I do call upon just suddenly, Cornelis, is here. He's mute and there's no.
Cornelis.
I just put you up.
Talk to Cornelis.
Yeah,
hey,
there you are.
Cornelis.
So, Cornelis, what's your take on this whole question? Or do you have any observations or questions?
Well, I've quite a different opinion of the existence of electrons and protons in the background, electrons and positrons in the background. I am pretty much an advocate of their complete annihilation and radiation off of energy and their generation when the energy comes together near the nucleus of an atom. It uses that nucleus as a catalyst to get the proper spins in that to generate the electron and or positron. So I'm not a believer of electrons and positrons being in the background, and I am an advocate of virtual particles, which I see as just interference points. Just like if you look out at the surface of the ocean or something like that, you've got bobbing peaks and troughs all over the place because you have interference patterns of the waves where you have real strong points.
That's a good way of describing it. That's a good description.
So that's what my opinion of virtual particles in the background are. There's constantly that interference pattern no matter where you go in space because there's waves traveling. So I said. And the thing about the electron and positron, I'm looking for, they have a charge, and I'm looking for a mechanical or a method to describe a mechanism to define why it is that there is a charge. Because I heard several people say that charge is not real. A charge is more of an effect, and I'm of that same opinion. Charge is basically a pattern which the waves take to cause a negative or positive attraction characteristic. There's always the question in my mind, though, you could say an electron attracts a positron, and I have the question of what's the mechanism of attraction. What's between them that caused the attraction, and or repulsion. So I try to look deeper than just accepting that the electron and positron are fundamental. And Andrew was making the statement I was interested in asking Andrew. He says electrons can scatter off of quarks. I do think that when they're talking about quarks being a mathematical tool, that's probably an accurate description in my view. That when you break a nucleus apart, the energy comes out, but it's going to come out in strong wave patterns and that. But the quarks are known to only be very temporary before they recombine. So again, it's this situation of extremely strong energy pattern that eventually, in order to be able to be stable, has to combine into a kind of a rotating pattern, in my opinion, or a resonant area of space in order to continue to exist. And I could see that electrons, which are themselves a strong resonant pattern, could be deflected, like a ship could be deflected or off of a high peak in the ocean or something like that. It had a tendency to have difficulty navigating over the peak, so it would be deflected around the peak. But it's still a temporary situation. So yeah, you would hit something that would deflect the electron, but it would not necessarily be. It would be a virtual particle. So like I said, mine.
There's a theory. Milo Wolf has a theory. It's very similar to what you just described. There's peaks and troughs, an electron and positron, or two electrons or two positrons, and he explains the attraction and repulsion in terms of the peaks and troughs. Milo
Yeah.
Wolf.
Well,
Yeah,
Milo Wolf is the first person basically agreed with my thoughts and that, and kind of he's just kind of the springboard from where I began actually. So I'm quite familiar with his work. Jeff Yee also has something similar to that, but I think he still has more of a particulate media that he deals with, and I'm strictly a non-particulate media where it has. I'm concerned about the bond between things, and so I wind up having nothing but a continuous bond media without particles. I'm looking for, even electrons and positrons. They're saying there's an attraction between them, but there's got to be a media carrying that attraction. So I'm looking deeper than that. So that's kind of where my opinion of this whole thing is. I'm also familiar with symphonies, electron positron lattice structure. And like I said, I'm not a fan of most of that. I think they are very good tools for quantitizing the amount of energy stored in the vacuum, in the space.
I think it explains the existence of Planck's constant as well, because if you have these tiny boxes, if it's 8 electron positron pairs on the side,
Right.
then
Yeah.
it can only
Exactly.
vibrate a certain way that agrees with Planck's constant.
Yeah. Basically,
that gives Planck's constant its value, I believe.
Right, but the distance
There's
between
no
those.
explanation for why Planck's constant exists in the standard model.
Exactly. That's what they're saying. But the distance between those and the strength of the charge and the magnetic field are basically calculated based on measurements of energy that we find between particles. And so it's working backwards to say, well, if we had a grid with electrons and positrons this far apart, and we would have the amount of energy we would find in vacuum space. So it's working backwards to put electron and positrons at a specific distance. And because of that, it can take that specific distance, which is actually the amount of residual energy in vacuum space, and rework backwards to go back and generate Planck's constant. So really, they're starting with Planck's constant with what is generated by Planck's constant, the electron positron attraction, setting it at the proper distance, and then turning around and saying, okay, that's why Planck's constant exists, is because these are exactly at this distance. So you're
saying this is circular reasoning,
back and forth. So it's not really predicting it; it's just regenerating what it came from in the first place.
Any response to that, Mark? It's a long.
Well, I think the existence of the lattice has to do with the permeability of free space, or permittivity, and magnetic permeability and electrostatic permittivity. Those two constants. I think that determines the structure of the. In fact, I think that determines the structure of the lattice, and then the structure of the lattice determines Planck's constant. I think Planck's constant is ultimately determined by those two fundamental constants. Related to the speed of light.
There again, you're taking the permeability of space, then you're turning around and you're generating a lattice that's the appropriate size to generate that amount of permeability. And then you come back and say, well, we can now predict the permeability because we have this lattice. So yes, I'm saying
the permeability and the permittivity determine the lattice, the structure, the distance apart, and then that determines the value of Planck's constant. Because they can only vibrate a certain way if they're a certain size.
And
the Planck's constant is ultimately determined by those two more fundamental constants. That Planck's constant is derived from that.
But you don't have an equation for that, do you? I mean, if you say it's derived
No,
from,
I don't. No, I don't. I'm just visualizing that that's the origin of Planck's constant, the value. That's why Planck's constant is what it is. I'm just visualizing that. I don't have any mathematical equation now.
okay.
I have a similar situation basically because Planck's constant, yes, it exists, but it basically exists because if you take a free volume of space and it's just like if you drop a rock into the surface of water, it will generate waves of a certain wavelength, and it will resonate at a particular frequency based on the surface tension of the water. Actually, rock would not be a good idea because the rock actually deals with
Gravity and surface tension. Yeah.
but your surface tension has a specific ripple length. If you have what do you call it? Capillary waves have specific lengths due to the tension in the surface of the water, and the same type of thing, and they will resonate to a point because of that tension, which is equivalent to comparable to your permittivity of free space, except for it's in 2 dimensions instead of 3. And so there's a resonant frequency at which those ripples in a capillary wave will occur. And the same thing will be true in 3 space. That resonant frequency determines the wavelength, the standard wavelength that space would generate from that resonant point. And that basically is your Planck's constant. It'd be the nominal wavelength that everything, the space resonates at.
Mm-hmm.
And so it's a different reason for Planck's constant rather than saying, well, there's a grid that determines the size of Planck's constant. This actually gives you, based on the permeability and permittivity of free space, it gives you Planck's constant as a fixed wavelength.
I suppose also it depends where you start from. I mean, it's a bit of a chicken and egg situation. You have to start from some constants. In this case, maybe permittivity and permeability and deriving other. But you could start maybe from Planck's constant, the elementary.
Yeah, one of them is fundamental, then the other one isn't. If you can derive them in terms of the other one, then they can't both be fundamental.
Right.
Well, except for Planck's constant, it has to be a measured value. You can't just pick a number out of the air and say that's Planck's constant.
It's measured value, but nobody understands the math to calculate it. It's too complicated. The math is too complicated.
Well, it's been done. It's been done basically from the permeability.
Oh yeah, I know it's been done from other ways, but you can't not from calculating the vibrations of the particles that compose the lattice. That's never been done, I don't think.
Yeah,
I know it's been done other ways.
And some further comment just about your non-use of the uncertainty principle, and maybe Kev thinks that's that's a bit suspect. But anyway, we have discussed that, and that's the difference between you. So thanks very much, Cornelis, for those comments. You're always quite incisive about things. Let me just see. Can I have to bring it down? Yeah. Okay. Now, okay. I'm just going to ask: is there anybody in the green room wants to come back further? So Denny does. Denny, you're back. You want to make some
in the Bergman and Allen electron and positron and proton modeling, the Planck's constant for all these 3 particles is what determines the fact that the gravitational mass of the particle is equal to its inertial mass. Because the gravitational mass is we're talking about a spinning charged ring here. The gravitational mass is the energy density of the electric field volume integrated over all space divided by c² to convert to a mass. where the inertial mass is the magnetic energy density integrated over all space and divided by c squared. So, and the fact that those two masses are almost equal is due to the fact that Planck's constant is what it is.
No, I've never heard that. I don't know anything about that.
Well, I saw that from your writings recently as well, but you know, it was something I had to give more thought to before maybe
Yeah.
pronouncing.
And I was going to go on a nice long walk yesterday.
Okay, there's some noise. Is that coming from your house, Mark? No.
Yeah. Wait a minute.
Okay,
Let me
no problem. No
let me
problem.
shut the door.
Yeah, no problem. Okay. Okay, Denny. So anything further before we just have a look?
Well, we've got 20 minutes, I guess.
Yeah, we actually have where we normally run out of time, but Mark was pretty precise.
I'm trying to think of anything more I can say about Sternglass. I just thought of something. It's the
Okay, well, go ahead. I'll bring you down, Denny, and let Mark.
Okay.
I'll give you the floor again. If you want to speak for another 5 or 10 minutes, that's fine.
The connection between Sternglass and Shimano. Now, I asked Sternglass by phone, did he ever hear of Shimoni? And he said no. I'm pretty sure they never heard of each other. But yet, they developed two theories where if you say that the elements that compose the lattice are electron-positron pairs, that's the reason why I say that in contradicting what Shimoni says. He says they're individual electrons and positrons, just like sodium and chlorine. But I'm saying no, they're electron-positron pair. Each one is a pair, they're identical. And the reason why I say that is because in Sternglass's model, those cosmological systems I talked about earlier, the electron-positrons that orbit around each other, the smallest possible one where you have two of them and they're orbiting around each other and the whole thing, the system has a mass of a single electron. That's the smallest possible cosmological system in Sternglass's model, and also the most dense. It's much smaller than a proton. It's much smaller and more dense than a proton, about 17 times more dense than a proton. That's what I'm saying is the elements that compose the lattice, electron-positron pair, the smallest possible Sternglass cosmological system. So this is amazing because it shows that Sternglass, you can use Sternglass's theory to predict the existence of the elements which compose the lattice in Shimoni's theory. And Sternglass visualized ether in a totally different way than Shimoni. That's one of their main points of disagreement. Shimoni visualizes the apolar, the electron-positron lattice, as a solid, whereas Sternglass visualized it as a liquid, or kind of like where they're free, there's no structure, either a liquid or a gas. That's how Sternglass visualized ether. So the fact that you can use his theory to predict the size of the elements that compose the ether, and also, as I point out in my essays, you can use Sternglass's theory to predict the elasticity constant of the ether. It's an elastic substance, which is why it's able to carry light. It's elastic, and you can predict the elasticity constant. It's very stiff, so it's very high elasticity constant. You can use Sternglass's theory to predict it. So that's another amazing coincidence, amazing connection between the work of the two individuals who never worked together. And I think that's pretty interesting.
Well, thank you very much for that addendum. And in fact, I might mention now that we have scheduled for the next talk in 2 weeks' time to invite Mark back again, where he will be going into more detail on Chimney. And I dare say you will touch on these aspects. You compare and contrast the two ideas.
Mm-hmm.
So we'll certainly look forward to that.
Yeah, Shimoni's theory. I'll talk all about that in 2 weeks.
I should know this. I apologize, but they're both deceased, are they?
Both what? Yes,
They
both died in the year 2015. And Shimoni was 93 and Sternglass was 91.
So this subject seems to be a good candidate to enhance longevity. If nothing else, it might complicate the mind, but maybe it's good for the.
Yeah, Sternglass, ironically, he was more passionate about his anti-nuclear work than he was about his physical theories.
Okay.
That was the main passion in his life.
You mean anti-nuclear disarmament?
Anti-nuclear, yeah.
Yeah.
Fukushima, atomic radiation.
Using nuclear power for civil means and then something going wrong, rather than say, ban the bomb.
Right. Yeah, he was worried that the nuclear reactors were not safe.
Okay. Okay. Right. Well, there are some comments still coming in, and if you want to cast your mind on them before we wrap up.
I don't see any comments.
Yeah. Well, see, are you looking at the private chat or the general comments?
I'm looking at the private chat.
The private chat, nothing has come in.
Well, read me some of the general comments.
Yeah. Okay.
I can't see them.
Okay. Let's see what's come in. There was one about this thing. Andrew, with what you mentioned earlier, that's where he mentioned the thousands of particles. Let's see, can I get that original comment? It's way back here. Protons and antiprotons can also annihilate into thousands of photons, kaons, protons, electrons, etc. in a single interaction. This is explained by hadronization of quarks. So you probably don't have that much time for.
No, I understand. I understand that much about quark theory, and I just feel that Sternglass explains it better.
Yeah. Okay. Well, that's a fair enough response. And there are quite a number of comments come in, but they're mainly just aside. Some of these are He's made a further comment here. Protons are dynamic objects that can get flooded with quarks as you increase their energy. So when you collide them at high energies, you can get dozens, hundreds, thousands of particles. Yeah. Okay. So, I mean, Sternglass's work is probably not generally known because it's slightly contrary to the mainstream explanation of these matters.
Mm-hmm.
So,
yes, that's true.
So actually, if nothing else, this talk that you've given us, and perhaps the next talk, will bring to the attention of many of our participants, mainly on the social media, the existence of these ideas, and maybe will prompt them to study more, and perhaps come back to
Sternglass's book is available from Amazon, called Before the Big Bang. It's available used for less than $10.
I was just about to ask you, is it expensive? No, that seems fine.
Another good book. This is one of the best physics book I've ever seen. Survey, Moses, and Warrior, Modern Physics.
Right.
And I use that in my book in my paper about the Larmor precession. Yeah.
Okay, maybe a last general question. Again from Andrew, does Sternglass predict any experimental results in high energy nuclear physics?
Well, he did back in the 60s when he said he was working at Stanford with Robert Hofstadter. They had a half-mile long linear particle accelerator, and he said it was in effect a powerful electron microscope, and it was the first one of the first accelerators with enough power to see the internal structure of protons. So that would be considered high energy nuclear physics. And he had those experiments. He was part of the experiments back in the 1950s, doing the original experiments on the original accelerator at Stanford. And Hofstadter won the 1961 Nobel Prize for that work that Sternglass and also Seth Nettermeyer was involved in. Nettermeyer's an interesting character too.
Do you know if he
and one of the
influenced
characters,
Alfred and Lerner?
what?
Do you know if he influenced Hans Alfven and Eric J. Lerner?
I don't know about them. I don't know what they're all about. I've never heard of them actually.
Yeah, Alfven is an interesting character. You could check that up. Yeah, maybe in Wikipedia even. Okay, well, I think we're going to have to wrap up within the next few minutes.
Yeah,
So,
great. I've been such a pleasure.
well, the pleasure has been all ours. Yeah. I just, the last one is just a comment really of Andrew again. So Sternglass theory can generate a spectrum similar to what was measured at SLAC. Perhaps.
Yeah.
So,
He was a part of the original. They have one now that's 2 miles long, but this one was half-mile long, I think, or 500 feet or something. He worked on the original experiments in the 50s.
And question is just telling us that Lerner wrote the Big Bang never happened.
Yeah, I know that some of the alternative theorists believe that, but I think it's incorrect. And I think the main proof of that is the delayed mini bangs, the quasars. They're exactly the same as the Big Bang, except a smaller amount of energy. And that's another prediction that Sternglass's model predicts, that quasars have the power inside themselves. They're more like white holes. There's not. The official explanation for quasars is a massive black hole is sucking in matter and shooting out radiation. Well, that's not. They're more like white holes, according to Sternglass. I think the standard model's incorrect in their explanation for the power of quasars.
Okay. Well, just before I bring you down, and I'll just close the meeting officially, any last words you want to say, brief words?
No, it's just been a pleasure, and I'm looking forward to doing it again next time.
Okay, well, I'll summarize that now. I'd like to thank Mark very profusely on behalf of all of us for having taken the trouble to give us this exposition of Sternglass's work. I think work with which we're not terribly familiar. I can certainly speak for myself in regard to that. And we're looking forward to his very kind offer to come back to us and give us a further talk on Shimony, whose name I'm pronouncing now in that way, having heard it pronounced by Mark. So we look forward to that. Now, for my own part, which is neither here nor there, I've always been very cautious of imputing physical models on the atomic scale. I mean, if we work in sort of macroscopic dynamics, one can get the forces and the equations and all that. When one goes to the atomic scale, we're only indirectly finding the effects of supposed particles. And whether those particles are real or whether they're just, as Gell-Mann himself said about the quark, whether they're just mathematical constructs which may or may not be real, is really a moot point. It's open to question. I've sometimes dismissed the whole thing as saying, well, what is matter, never mind. What is mind, never matter. So one can get into very, very deep conversations about this, and the chances of being in error are quite strong. So therefore, if I have to make some sort of reconciliation between the various comments coming up, I would say that both in the mainstream and in the dissident ideas of atomic physics, there's a very, very great chance of both of them being wrong. So I leave it at that. But again, thank you very, very much, Mark, for the trouble. I'd also like to thank Denny for, first of all, he's worked in this area, but for his last minute agreement. I mean, Mark was a few minutes late because of the computer problems. These things happen all the time. And I'd like to thank very much Denny for having come in and offered to talk to us on that. We'll keep that as a sort of a possibility of coming back to. And also Laurie Gardy, who was familiar with this work. And in fact, not only was her kind invitation taken up by me to give an introduction and to tell some personal details about Sternglass, including the diminution of his ideas about the advantage of postgraduate study, but also my keeping Mark, because as soon as he came in, I did keep him for 5 minutes to allow Laurie to continue. So thank you all very, very much. And again, mostly I must thank Mark for his talk, and we hope to see him back in 2 weeks' time. But again, nothing is definite until the notices go out. So just keep an eye on the notices, and we look forward to having your contributions again. So I'll close the meeting now, and I'll just wish you all, wherever you are in the world, a very good day.